Okay, so it means that there's no acceleration, which means, see, if I were to calculate the slope, no acceleration, which means you don't really have an acceleration time graph because the object's not accelerating. It'd be like if you were driving down the 401 and you put on cruise control, right? You're just going to drive at a constant speed for X amount of time, right? And you could figure out how far you drove based on that motion, right? Because there was no acceleration going on, right? In the question that we did this morning, you saw this little chunk in here. This is where this conversation came from, right? Where we saw that there was some form of acceleration, whether it was slowing down or if it was speeding up, right? That's going to change the way that the graph looks, okay? And so to figure that out, you guys could calculate the slope of the graph, okay? And then the other way you could do this, so if you were let's say given an acceleration time graph, you could again calculate the area, and then you could calculate the area again, right? You could do it twice to produce the graphs, okay? Is everybody okay? Sometimes if you insert pictures in my iPad, it goes a little bit funny, okay? Okay, so these would have been the graphs from this morning. We saw what happened, okay? So let's go down. I just want to run you guys through one of these, right? And we can do the one that we know how to do. So if I put like let's say, or maybe I'll try and do this in red so you can see it a little bit better. Position, right, in meters, and this will be in the direction of east. All right, it's hard to write sideways. Okay, and along the y-axis, so we'll put we'll draw our y-axis along here. We'll put time, okay, in seconds. Okay, we saw this morning that we calculate the areas of each of these shapes, right? And that's how we figure out what the position of the object is going to look like. Okay, so it looks like for this area here, for the red area, we're going to have 2 seconds. So we're going to have 15 meters per second. And we've got to multiply that by 2 seconds. So how far did the ball, or whatever this is, travel in those 2 seconds? It would have been 30 meters. Okay, so we need to produce an axis up here. Okay, so we're going to have 10, 20, 30. Okay. Are we okay? And then, like always, I suppose we should draw in wherever there's kind of like, we'll call this like maybe an inflection point or something of an interest, right? Something interesting is happening. We'll say, like for instance, like a change in direction would be like an inflection point or something, right? So wherever you're seeing the graph kind of change, you guys can draw some like a dashed line up, right? And that'll help you identify where to draw your points. Okay, same thing here. Like, you guys don't know it yet, but from here, something interesting is going to happen here. Okay, so just draw a dashed line up for that one as well. Okay, and then the end of the graph, you could put a dashed line as well. Okay, just so we can see. Okay, so for the first 2 seconds of the motion of the ball, for the position, we saw, because we just calculated, we should expect to see 30 meters, right? The ball traveled 30 meters, so you're going to have a point at 0, and then it's going to go up to 30. Okay? And then we see, oh, I see this triangle here. Okay, well, let's do the area of the triangle, and let's say purple or something, okay? Okay, and so let's figure out what the area of that is. Okay, well the area of that purple section is 1/2 the base times the height, which is going to be 1/2 of the base, which is going to be the difference from 8 to 2, which is going to be 6, right? 6 seconds have passed here. So it's base is 6, and the height is 15. Okay, so you guys will see it'll be 1/2 times 6 will be 3. 3 times 15 you should be 45 meters. Okay, I know it's meters because for the same reason on the same reason as here, like I'm just matching up the units, meters per second and seconds. Whenever I multiply a speed times an amount of time, I'm going to get the units of meters out. Okay, so that means, okay, well I can go up to my graph and I can plot, okay, we're measuring the distance traveled by the ball, like the position, right? So it's already traveled 30 meters. So I've got to add the 45 that it has now traveled in this second purple section, right? And so we're going to go 30 plus the 45. It's going to come up to the 75 meter mark, right? Right here. Oops. Where'd it go? Okay. And then, just to save us some trouble, maybe not actually. Nope. We're going to calculate the area of this last chunk, right? It'd be, we'll call it the green piece. Okay. How do I calculate the area of a triangle? We say, okay, well the area equals the 1/2 the base times the height. Right, and so I'm going to get 1/2. The base looks this time 8. We're going to go from 8 to 16. Well, that's 8. And the height is going to be negative 20. Negative 20. Okay, can we see that? And so we're going to calculate the area. We're going to get, okay, well that 1/2 of 8 is 4. So I'm going to get 4 times 20. It's going to be 80. Negative 80. See, I'm bad for negatives sometimes. Negative 20. 4 times negative 20 is negative 80. Is that okay? It's starting to get a bit messy. Sorry, guys. Well, that's not too bad. Okay. So what's that mean? Well, remember we're adding the areas, right? So the area here was negative 80. Well, I had 75 on this first piece. Okay? Which means we should be down in the, we'll start to get a bit messy. -5 territory. Okay? And then we can plot the points on now. Right? I know one of these points is 0, 0 because it started at 0, 0. Then it went up to 2 and 30, right? And then we went up to, this was 8 and 75. And then we went to, we're going to have 16 and -5. Is everybody okay? The last part of this, to produce this position time graph, is to connect the dots. Okay, so as long as everybody's okay, we're going to see what the kind of motions we got. We got to pay attention to the motion, right? So for the velocity time of the first part of this graph, right, there's no slope, right? So we know that it's moving at a constant rate. It's not accelerating, it's not decelerating, right? So there's no curves. There's no curves because, like what we saw this morning, right, on this question, because I don't have a slope. There's no slope, it's just constant. So it's just a straight line in the position. It's moving away from the origin at the constant rate. So it's just a straight line. Okay, so from here to here is just going to be a straight line. Now, the slope here is negative. Okay, for the same reason from this morning, it's slowing down, right? And it's slowing down as it approaches this point here, right? So we know that if it's slowing down, then its position relative to time is decreasing, right? And so we should expect to see kind of a, I'll try to draw this as curved as I can. Okay, we know that it's curving down because it's slowing down, right? The amount of distance that it's covering per unit time is decreasing. Now, the reason why I highlighted this point here in the middle was because it's at that very moment in time. If we looked at the speed or the velocity at this very moment in time, what's it telling us? Maybe drop it in the chat. What value is on the graph? It's okay. Jagger's right. It's not moving at that very split second. Very small amount of time that it's not moving. So its velocity is 0, right? That's what the graph's telling us. The velocity at this point is 0. No velocity, right? And so if you guys remember when doing some quadratic work in grade 10 or in grade 11, whenever you like the 4 C's would have taken it in grade 11 and some of, well, it's grade 10 too. You'll notice when we threw a ball, there was a small portion of time when it reached its maximum height where it was no longer, its velocity was almost 0. Like it had a turnaround point, right? If we threw a ball up in the air, it's going to reach a maximum height, and then it's going to turn around at that maximum height and come back down. In that very split second, it's not moving. Okay, that's what that represents. But the green portion of this graph is now the motion of the ball coming back down, right? And it's accelerating because gravity is pushing on it, right? It's causing it to accelerate. It's getting faster and faster and faster, right? And so the graph for this one, for the green section, I should have done it in 2 different colors, is accelerating, right? It's moving faster and faster in the negative direction as time goes on. That's what it's telling you. It's almost like an exponential, which most of you would have seen, right? As time goes on, the amount of money you make gets faster and faster and faster. This would be accelerating in the positive direction. Okay, this is accelerating in the negative direction, right? The numbers are getting higher and higher and higher as time goes on. So accelerating. Is that okay? So that's really just this morning's lesson, right? That's a mapping of what the ball would look like or whatever got thrown. Okay. Now, acceleration time graphs are kind of easier, but not really. Okay, they're simpler to draw. Okay, in the very moment, let me just draw some units on here. We talked about what the units of acceleration would be. Acceleration would be in meters per second squared, and this is still in the eastward direction, right? Positive up and positive up, and negative would be in the westward direction. Okay, so what we've got here, I'm going to draw a graph, right? And this is going to be 0. And then we're going to have, just because you guys will see in a minute, sometimes you'll have to do this work first before knowing what the axis is going to be, right? We saw above, and this is no different than what you saw this morning, okay? It told us above, if I'm given a velocity time graph, and the velocity is not constant, so it's not a straight line horizontally, so that there is some form of slope, then we know that the object is accelerating, okay? And if there is a slope, then you can calculate what that slope is. Whatever that number is what goes on your graph, okay? In the form of a straight horizontal line. Okay, grade 12s, the 4U's, we will see an instance where acceleration is not constant, and that is something else. That's for a later unit. Okay, but for the grade 11s, you don't need to know that. Okay, that's for a grade 12. So anyway, we have this velocity time graph. If I were to calculate the slope of the graph, that is the acceleration. The slope of the velocity time graph is how the velocity is changing relative to time. That is acceleration by definition. Okay, if it's negative, it means it's slowing down. If it's positive, it's it's speeding up, right? And so what we've got here is we've got to calculate the slope. So initially, do we have a slope right here? Right? I don't see any slope there. Right? So you guys can extend, as you do these questions, you can extend your inflection points. Yeah, everything's recorded, Carter. Yeah. All the videos that I post are all like, they're just the recordings of the live lessons. Okay. Okay. And so you guys, you can extend this. This one doesn't matter too much. Okay, but you can extend them backwards, and we know for the first 2 seconds of this ball's flight or whatever it is, right? There's no acceleration. So your graph is going to look like this. No acceleration. It's 0. It's got a value of 0. Right? Then, once you guys find the slope, right? I'll try to clean this up here. The slope for this portion of the graph, right? You're just going to find the rise over the run, right? So for the purple section, rise over run, what do we get? Well, let's just pick some points here. Let's say we'll pick 1 to be 0 here. Right, so one of them is going to be at 0, y2. So 0 minus, what was the initial value? 15 over 8 minus 2. Okay, because everybody see where those points came from, right? So 1 point here would be 0.1 would be 2 and 15. And 0.2 would be 8 and 0. Okay, and that's how I plugged it in. y2, that's not y squared, y2 minus y1 over x2 minus x1. Okay, and we get a slope. We get negative 15 over negative 6, which we're going to find to be, positive 6. What is that? 12, that's 2.5, negative 2.5. Yep. All right, so we go on our acceleration time graph, and we know acceleration is going to stay constant, right? Like we know that the acceleration is not going to change, right? We just know that it's constant, right? And so constant means a horizontal line, right? So at 2.5, negative 2.5, the acceleration is like this. Okay, now you ask yourself, well, what's the how do I connect these graphs, right? Well, it just looks like this. You just connect them like this. There's such a small instance of time where the change in acceleration happens that you just connect them. Okay, and then you got to ask yourself, okay, well, what about this green portion of the graph? Well, if you found the slope of this green portion of the graph over here, it's also going to be negative 2.5, right? So this is what your acceleration time graph would look like for this. Anybody have any questions? Not the easiest thing in the world to wrap your head around. My advice would be, don't make sure that I would do the work, like find the slope and things before you label your axes. That would be one tip. But I would say if you're going downwards is slope. Like, you guys see that? No, that's horrible. Let's do it in like a pencil. I would say if you guys are going downwards, it's slope. If you're going up, it's area. Same thing here. Down is slope. Up is area. Okay, I'll give it a minute here. If you guys want to drop anything in the chat, if you're freaking out about it, I know it's getting a little bit messy. Hopefully yours, when you put a nice grid paper in front of yourself, if you print these out, it looks a little bit better. The iPad gets a little bit funny. You guys could even shade these things in too, right, to help yourselves. Yeah, I'll wait a minute, because this is sometimes like cumbersome for some people. Not easy. If you just remember, like, I think when I learned this the first time, I had zero appreciation for what was happening with the units. If you look at the units, you can't mess this up, right? Rise over run. Rise over run for the part. Like, every time you do rise over run, if it's meters over seconds, that's going to take you to the velocity graph. If you do it again, you're going to go rise over run. You're going to get meters per second. I'll write this like this. Over seconds. Right? If you take the slope. Well, how do I simplify this? Well, you bring it up and multiply by the reciprocal. Meters per second times 1 over seconds. Well, that turns into meters per second squared. This is acceleration. That's how I never forget. Slope gives you the division, right? Whereas multiplication is area, right? That's going up, right? And that starts canceling units. That's how I remember this. Okay, is that helpful for anyone? Sometimes I appreciate if you guys throw things in the chat too, right? That doesn't make sense or whatever, right? Just to give me a gauge. Okay, I can do one more. There is like, well, I think I have enough time. We can do one more. We can do the other one. There's a bunch posted online as well. Okay, for practice. There's some kind of questions too. Okay, so I'm just going to try and clear some stuff up here just so it's a little bit neater. Okay. And we'll do the second question. Okay. If I ask you guys to do some of these on a test, like you get, like if you don't have grid paper or something, just draw it kind of as neatly as you can. Like if I showed you mine, like I'm okay with this. If you guys draw this and just do you see that? I took a ruler and I just drew some, like, nothing too crazy. Okay, there's no grid lines. It's pretty clear and neat. Okay, that'll do for me on a test too. You guys can see that. That's clear. Okay. Okay. We take a look at this one. So above, what I'll do is I'll try to draw this in here as neatly as I can. I'll thicken it up maybe so we can see it. Okay. And so we're going to call this our position time. Right? Position 1 always goes on top in meters. And I guess we'll call it east. It's hard writing sideways. If I try to turn the iPad sideways, it's going to rotate the screen too. That's the other thing. Time in seconds. Okay. We can see here, there's nothing interesting. Like if you guys are asking yourself, well, where do I draw these like inflection points, right? Well, you're gonna like anywhere there's a change in the graph, kind of, right? So I see that there's one here. Just draw a vertical line up, Draw a vertical line down, and we'll deal with the acceleration graph after, right? And then you do the same thing here. Oh, there's another change. Right? And you're like, okay, here this is starting to formulate the checkpoints for the graphs, right? So how do we go from velocity to position? Like, how am I going to figure this out? Well, you find the area in here. Right? What's the area? Well, the area for the green section, that's going to be 1/2 the base times the height. Right? So, oof, it's tight. What you're going to find, okay, well, the base is 2 meters, so it's 1/2 times 2 times the height is 6. Okay, so the 1/2 and the 2 cancel, you're left with 6 meters. Okay, well, we know so far we have to go up at least 6. So I would suggest before labeling this axis, if you guys are doing these, and this is why I try to do things with you guys, is that way we can kind of work out some of these, like exactly how you want to do these processes, right? Like you want to like figure out how to label your axis, what to count up by, right? I don't know yet. I don't know how high to go, right? And so you might want to do all these area calculations first, right? And then figure out, okay, I've got to add them all up and I know how tall it has to go, and then you just start labeling your axes accordingly, okay? So let's do the second one here. We'll say this one's in like red. Okay, we'll do the red section. Okay, well, the area of the red section is going to be something like, it's just a rectangle. So this one's kind of easy, right? The area is length times width for a rectangle. Well, we're going to get 2 seconds times, how tall is it, or width-wise, it's 6. Well, we're going to get 12 meters there. Okay, for the last little section, it's again a triangle. There's an orange. Okay, we'll just figure it out, right? You're going to go, okay, area 1/2 base times height. You get 1/2 times 1 times 6. 1/2 times 6, that's going to be 3. Or 6 divided by 2 is 3. So 3 times 1, that's 3 meters. Okay, so how high do we have to go is the question. All right. Well, we're going to have to go up a total of, you're going to have to add these guys up. 6 meters, 12 meters, that's 18. Plus another 3. You have to go at least 21 meters on your axes, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's say if I counted by 2s, it'd be okay, right? So if I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, okay? There you go. You know you only have to go up to 21, right? Because that's what these add to. So for the first chunk, you know, the first chunk of time, we're going to have 6 meters. Okay, so we got to go from 0, and we're going to go up to 6 right there. The nice thing about having these yellow lines here is you don't have to, there's no visualization counting over in the time direction. You just know that it's going to match up. So for the first 2 seconds, you know that they've traveled 6 meters. Okay. And then for the next one, we know that 6 plus 12 is going to be 18. So I got to go all the way up to 18. Right? That'll be the red section, and the last section in the orange will be the 21. Well, I suppose you guys could add in another, so you know where to stop. Just draw a yellow line up so you know where to stop on the end. Okay, so you're like, okay, well, how high up do I have to go for the orange piece? Well, just go to 21. Okay, now we have to ask ourselves, what's happening? How is this thing changing? Right, well, it looks like the slope is positive here, right? And so, like the slope, sorry, I'll be more specific. The slope for the green section here is positive. which must mean we know with acceleration, if I were to take the slope and it was positive, that means it's speeding up, right? It's getting faster and faster as time gets on, right? And so we know if I were to connect the dots for the green portion, we know that it's going to have to look something like this, right? Because it's getting faster and faster. Maybe not quite that drastic, but it's accelerating. It's getting faster, right? Because the slope is telling me it's speeding up, right? And then for the second one, well, the second one, we have a nice rectangle, right? For the red portion. So we know that the velocity here has no slope, which means no acceleration. Or I don't know why I didn't do it. Right? So if there's no acceleration, that's just that it's just moving at a constant velocity, so that the position graph should look something like this. It's moving at a constant speed, constant velocity. It's just getting further and further away as time goes on. It's not accelerating, it's just moving at a constant speed. That's what the zero acceleration means. Right? And then for the orange portion of the graph, the slope is now negative, right? Which must imply there is acceleration because there's slope. What kind of acceleration is it? Well, if it's negative, it's got to be slowing down. Well, what does the slowing down look like on the graph? It must look like this. Something like that. Okay, maybe not so drastic. I'm just trying to connect them. Okay, and you guys can draw on your points as well, just so that there is some form of reference. 0, 0. We're going to get 2 and 6. And we're going to get, remember, this is your area and the time. And you're just mapping area and time. Right? The time for this one would be 4 and 18. And then you're going to have 5 and 21. Those are your points. Anybody have any questions? This is not easy. Not easy. I think the most important thing is you guys keep track of which direction does the area take you and which direction does the slope take you. That's probably the most important thing. Okay. Now we're going to do one more part of this. We're going to figure out what the acceleration graph looks like. Okay. So let's just draw that. Okay, well let's come down here and we'll draw what the acceleration looks like. Create a straight line for me. Okay, so this will be the acceleration. Okay, well, how do we do that? How do I know? Yeah, okay, we're okay. I'm going to erase this bottom line here for a sec because we got to make a difference here. It should be somewhere in the middle. I know it has to be somewhere in the middle in case you guys are wondering. It has to be somewhere in the middle because I have both. I have positive accelerations and I have negative accelerations. So I'm going to have portions of the graph up here and I'm going to have portions of the graph down here. Okay, that's how I knew that. Okay, so that's what I mean by like maybe before you guys draw this thing down here, and this should be on me too a little bit. I haven't done this in a while. Let's figure out what the slopes actually are, right? If we know what the slopes actually are for each of the sections, then we know how to like label our axes and things like that, okay? So for the green portion, we'll look at the green portion of the graph, right? So pick 0, 0, and 2 and 6, right? So the slope there, you guys could probably count this up too, right? Like if the graph's nice, you don't always have to do this formal slope calculation. You can look, okay, well, what's the rise? 1, 2, 3, 4, 5, 6. I got to go up 6. And then I've got to go over 1, 2, 3, 4. Oh, I got to go over 4. Well, what is that? 6 divided by 4, you could figure out to be, is it? Oh, sorry, it's not 4. Pay attention. So the only thing, it's good that I do this sometimes too, right? It's not 4. There's 1 and there's 2. 6 over 2. That's 4 boxes. But just pay attention to how you've counted on your axes. That's good. Okay. Well, 6 over 2. Well, that's 3 meters per second squared. Well, where's 3 meters per second squared, you say? Well, okay, well, maybe we'll put it up, maybe we count by 1, 2, 3. Well, 3 meters per second, that's going to be here. For the green portion of the graph is going to look like this. For the first 2 seconds, that's what your acceleration looks like. It's constant acceleration, right? For the first 2 seconds, right? And then we know for the red section, there is no acceleration, right? You just got the, so we know that it's 0. And then for the last section, you guys could do the same thing, just count it up, right? You know, we've got to go down 1, 2, 3, 4, 5, 6. We got to go down 6 and over 1. So that's 6 meters per second negative. So you might have to count down to -6 there. -1, -2, -3, -4, -5, -6. So there you go. There's your acceleration for the last little portion of the graph, this little skinny. Here, I'll extend these yellow lines down. So for the last little portion of the graph, the orange portion, your acceleration will be, how do you connect these all together? Well, ideally you do these all in one color. And you just connect them. They'd look like this. Right? If I did this all in one color, you'd just have this. Something that look, the graph would look like this for an acceleration time graph. That's what you would have. Anybody freaking out? That's not an easy brand new concept. Okay, but particularly the acceleration, because we haven't done the acceleration yet, but that's what we're going to do tomorrow. We're going to see how acceleration affects things. Only, I forget what I asked. Only slightly. That makes sense. It'll take a little bit of practice, but the homework questions that I put up as well, there's a little bit of a reading that you guys can go through, and it'll spell everything out as well. Okay, and then there's some homework questions, and I believe that there are answers in that document as well. Okay. Remember, the only difference from this morning to this afternoon is the addition of the acceleration time graph. Okay, so just this stuff down here. If you were okay with this morning, that's just, you're just going from velocity to time. You're just finding areas. Well, if we come down, we're going to find the acceleration. How velocity is changing relative to time is acceleration. That's it, what it is by definition. Okay. So just before we go here, I want to run through one of these. This is a position versus time graph, or like a displacement graph, right? And what we want to say here is we just want to identify, and what I'll do is I'll do these in different colors. Again, same thing, okay? So for section A, we just want to talk about how the object is moving, right? We just want to talk about how it's moving, okay? So if you guys were to take slope, like the slope of that, it's a curve, right? So this is not it's not a straight line like section B. Like I'll jump to section B here for a second. Section B would be very easy to take the slope of, right? We just find the 2 points and find the slope. That's rise over run. The problem with section A is, and we have these things, if I were to find the slope is ever changing, right? Those little black lines are what we call tangent lines, right? And they're telling us how the rate of change is, what the rate of change is at a moment in time, right? But the fact that I can't draw one black line there tells me that, if you guys think back to this morning, finding the slope of this purple line would tell me the velocity, which would be easy. You could be able to do it no problem, right? But the problem with section A here is that I don't have just one black line. I have 3 or 4, however many tangents, right? And so that's saying that the velocity is changing, right? There's no constant change in the velocity. Okay, so for section A here, we know that it's moving in the positive direction. It's moving okay. Now, what we also know is its velocity is changing, right? Relative to time. How is it changing? Well, is it curved up or is it curved down? That's your last question. Curved down implies that it's slowing down or decelerating. Curved up means it's accelerating. Okay, so we know it's changing relative to time, so it's positive, so it's accelerating. Okay, section B. Is everybody okay with that? That's not an easy first little part to this, but everybody okay? For section B, it's a straight line. Okay, so we know for section B, good, thank you, yes. And then so for section B, we know it's moving at a constant velocity. In the positive direction. Okay. For section C, do it in orange. We've seen this already today. Same thing as section A. You know, the velocity is changing because it's curved. So we know that for section C, we know it's still moving in the positive direction, right? I'll write the word. But what's happening? It's not moving as quickly relative. You can see it clearly with section A, right? Like section A, it's going faster and faster and faster. Well, for section C, it's slowing down, right? And so it's still moving in the positive direction, but it's slowing down. Okay, and then for section D, it's not moving at all, right? You can see its slope is 0, right? Which means its velocity equals 0. If you don't have any velocity, that means you're not moving, right? If you think of it relative to the distance time graph, the distance is not going up or down. It's staying at 0, which means you're standing in one spot. You're standing at this distance, which whatever it would have read off here, right? If let's say it was 10 meters, it means you're standing at 10 meters and you're not moving for, I don't know, 4 seconds or something. Okay. I'll get rid of some of that. It's just going to make things messy. Okay, so for section D, okay, section E, I'm running out of colors. We'll go till I run out of colors. Section E, they've turned around. They're now moving in the negative direction. But they're speeding up, right? They're accelerating. Right? And we can see that because the rate at which they're speeding up, right? They're getting faster and faster. Section F. Here's purple. Gray. You guys see gray? Okay. They're moving at a, oops. moving at a constant velocity, right? Because it's a straight line in the negative direction. And then for point G, brown, they're slowing down, still moving in the negative direction, but they're, we'll say, decelerating in the negative direction, right? They're slowing, and then they would have come to kind of a stop momentarily between G and H, right? Oh boy, what color am I going to use now? Right, so they would have come to a moment. You see that okay? Not great. Momentarily stop to change direction between G and H, and then they move. I shouldn't have picked yellow. That's horrible. Move with a constant velocity in the positive direction. Okay, and so what we call this is, this morning we would have had uniform motion, and this would be non-uniform motion. Okay, where things are accelerating, right? That's non-uniform motion. As soon as you introduce acceleration, that's no longer we just moving at the same rate all the time. That would be uniform motion, right? Whereas now things are changing, we have accelerations, we can figure out what those accelerations are, and that's it. Okay, does anybody have any questions? You feel free to ask them. Okay, I'll stop that there.